sorts of measurements you can do. So first of all, you can't do a measurement that tells you precisely what the object state is. It's the one that resolves all four of those guys. But you can do these sorts of coarse-grained measurements here. So you can do the measurement that distinguishes 1 or 2 from 3 or 4, and you can do a measurement that distinguishes 1 or 3 from 2 or 4. So those we also saw were part of this restricted statistical theory of a bit. But the third measurement that we saw in that theory, where you distinguish 1 or 4 from 2 or 3, that's not allowed in this world. Okay? All right, well, it turns out that this is exactly the sort of world that you'd want to live in if this task was important to you and you wanted to succeed well at it. Because there's actually a protocol that'll give you probability success 1. So what Alice does is she takes the 2 bits, the victor and center, encodes them into the preparation. So, she just uses a binary encoding of this integer. 0, 0, she does this, 0, 1, she does this, and so on. And then if Bob wants the first bit, he does this measurement because 1 and 2 are the 0, 0 and the 0, 1 state. So the first digit is 0 here. The first digit in this case, these are the 1, 0 and the 1, 1. The first digit is 1. So this tells her what the first bit is. And this measurement tells Bob what the second bit is. So he just finds y for Victor, chooses to do one of these 2 measurements, and finds out exactly, with probability 1, the bit that he's looking for. And now the key thing is that in this world, there's also no measurement Bob can do that would tell him anything about the parity. Because this is the measurement that would reveal information about the parity. It would distinguish the 0, 0, 1, 1 states from the 0, 1, 1, 0 states. And those are the 2 that have different parities. So in this kind of world, you would win all the time. But now there's sort of an odd feature of this world we're imagining, which is that in addition to these extremal preparations, the ones where you have as much knowledge as possible, you can always make some other effective preparations. So for example, you can mix this guy and this guy with probability half each. You get this distribution. Or you could mix this guy and this guy with probability a half each, and you get this distribution. So there's 2 very different preparation procedures which give that have these representations in the ontological model. And what's interesting is that no measurement you do can tell the difference between these 2 probability distributions, because they're both going to give probability a half for the 2 outcomes of each of these measurements. This measurement would allow you to distinguish them perfectly, but it's not allowed. So in this theory, you have these 2 distributions that are totally indistinguishable at the operational level. All measurement statistics are the same for them. And yet, they're completely different at the ontological level, the hidden variable level. In fact, they're disjoint. And so they're as different as they could possibly be. They're sort of maximally distinguishable at the ontological level. And that is exactly how we define the notion of preparation contextuality. If it were non-contextual, then things that were indistinguishable operationally would be indistinguishable at the hidden variable level. And here they're not. So we've seen that here's at least one world where the failure of preparation on contextuality is responsible for the better performance on this task. So before I show you how that generalizes, let's look at what happens in the quantum world. So here's a scheme that can give you probability of success approximately 85%. So 1/2 plus 1 over 2 root 2. And the idea is that Alice gets the 2 bits from the verifier, and she encodes them in one of 4 states of a single qubit. So this is just a plane of the Bloch sphere. And these are 4 states on a square in the Bloch sphere. And she prepares whichever of these corresponds to the bit string she got from Victor. And then Bob, if he wants the first bit, does this measurement here. And if he wants the second bit, he does this measurement. And so if you look at it, if Alice, let's say, encoded this one here, then Bob is more likely to get this outcome than this outcome. So he guesses that the bit had value 0 if he gets this outcome. And if you work it out, he guesses correctly 85% of the time. Similarly, if he wanted the second bit, then he's more likely to get this outcome if the second bit was 0. He's more likely to get this outcome if the second bit was 1. So he guesses 0 here. And again, he gets probability 85% of guessing correctly. So no matter what Alice has encoded and no matter what Bob measures, his probability of guessing correctly is 85%. And so that's the success probability overall. And then finally, you have to verify that the protocol really is parity oblivious, satisfies that constraint. And the reason for that is that if you consider the parity zero state, which is the equal mixture of the parity zero preparation, 0, 0, 1, 1, it's the completely mixed state. And the parity one, which is the equal mixture of this and this, is also the completely mixed state. And we know in quantum theory that there is no measurement. If I have two preparations that are both represented by the same density operator, there's no measurement that will yield different statistics for that. So there's no measurement Bob could do that would tell him anything about the parity. And so yes, it is parity oblivious. I should mention that this protocol was one of the very first quantum information protocols ever developed. So it was actually developed by Stephen Wiesner in the late 70s. It wasn't published until the 80s because apparently no journal would accept it. This connection with the parity oblivious property wasn't relevant to him, so he didn't emphasize it. These days, people do look at these sorts of schemes, these multiplexing schemes, but they tend to be called random access codes in the literature rather than multiplexing. So that's the key word if you're interested. So now we've seen two examples of theories that are preparation contextual. Well, actually, I haven't convinced you that this is preparation contextual. I'm going to do that next. We had other reasons for thinking that quantum mechanics is preparation contextual. So it leads you to think, well, maybe in this game, to do better than you can in the classical world, you need to be preparation contextual. And that's right. So what I'll show you is that for all operational theories that do have a preparation non-contextual model, the probability of success in this game is always bounded above by 3/4. So whether you're a classical theory, which is preparation non-contextual, or some other theory, you'll never do better than 3/4. So this is like that Bell inequality we saw for the probability of success in the PR box game. But it relates not to locality now, but to non-contextuality. It says any preparation non-contextual model will satisfy this inequality. So we can call this a kind of non-contextuality inequality. The left-hand side depends only on the experimental statistics, and it says if you can model this in a certain way, they'll have to satisfy some constraint. Yes?
Regarding not giving out information, but is it just a restriction? Is that for any possible measurement that Bob can do?
That's right. Not just the two measurements that the protocol tells him to do to get bit 1 and 2, but it says it doesn't matter what you do. Even if you don't do one of these two measurements, if you do some other crazy measurement, you will still never find any information about the parity. Okay, so let's go through the proof. And it's a derivation of a non-contextuality inequality in the end. So now we're in the context of a general operational theory, and we can still talk about preparations and measurements. And we know that whatever protocol Alice and Bob use, Alice is going to have to choose 4 different preparation procedures. One for each possible pair of values of the bits that Victor sent. So I'll just denote those this way. And so the protocol will run, if Victor sends her 0, 0, she does this procedure. If something else, she does something else. And we could be in quantum mechanics, we could be in some other theory. Over here, Bob is going to do one of 2 different measurements depending on the bit that the verifier has sent him. So I'll call those M0 and M1. And without loss of generality, I can assume that each of those measurements has only 2 outcomes, because in the end, he only needs to send a bit to Victor. And so if he had chosen a measurement that had more than 2 outcomes, for each outcome, he would have to decide, am I going to send 0 or 1 to Victor? And so you could always coarse grain up all those outcomes where he was going to send 1, coarse grain all the outcomes where he's going to send 0, and call that a new effective measurement, which now has only 2 outcomes. So it's enough for him to have 2 binary outcome measurements. Okay, good. Now, the next thing we can do is define some effective procedures in terms of those 4. So the parity 0 procedure is the one where you implement P00 with probability half and P11 with probability half. And the parity 1 procedure, which I'll denote this way, just corresponds to the equal mixture of P01 and P1 So of course these, this is just a mixture of procedures like we've seen many times before. I can always define these no matter what operational theory I'm dealing with. And the constraint of being parity oblivious is just this. It says no matter what measurement you do, so not just M0 and M1, but any measurement at all that this operational theory allows, it better be the case that the probability distribution over outcomes for that measurement is exactly the same whether you've done the parity 0 or the parity 1 preparation. If this weren't the case, then by doing that measurement that made this unequal, you would learn something about the parity of the preparation. So again, I haven't referred to the quantum formalism here at all. Okay, now here's the critical step in the proof where I actually apply the assumption of preparation on contextuality. So you'll recognize this statement here as a statement about operational equivalence of two preparation procedures. The last time you saw it, it had a P and a P prime here. And what the assumption of preparation on contextuality told you was whenever two procedures cannot be distinguished experimentally, you should represent them by the same distribution over the hidden variables in your ontological model. So we're just applying non-contextuality to this particular pair of procedures. And so it says if you had done this or this, you should expect the same distribution, or you should assume the same distribution in your model. Okay, so now it's very easy to get to our inequality. The first thing we do is just a Bayesian inversion. So remember Bayes' theorem, probability of A given B is the probability of B given A times the probability of A over the probability of B. So if I just multiply this guy by the probability of the parity 0 preparation and divide it by the probability of lambda, that'll give me this term. But the parity 0 and the parity 1 preparations have the same probability. It's a half each. So that's, I can cancel those guys out. And the probability of lambda is the same because I would just sum over each of these guys here. So in the end, I just find that given lambda, the probability of parity 0 and the probability of parity 1 are the same. So if I learned lambda, I wouldn't learn anything about the parity. Just like up here, if I learn the parity of the preparation, it doesn't teach me anything about lambda. Okay, and now we're basically back to a kind of classical protocol because lambda is the physical state of whatever system Alice is setting Bob, the ontic state in the ontological model. And this is telling me that it cannot encode any information about the parity. Even if Bob could learn exactly what lambda was. In general, in these ontological models, you can't. All your measurements are very coarse-grained. But suppose that Bob could do a measurement that would teach him everything about lambda. This says, even then, he would learn nothing about the parity. Because the probability of estimating parity 0 and estimating parity 1 is exactly the same for every value of lambda. So now we're back to what if Alice sent Bob a classical message? So lambda is effectively a classical message because the underlying ontological model is just a classical model. So we're asking if Alice is allowed to send anything to Bob, any classical thing to Bob, which encodes some information, but cannot encode any information about the parity, how well can she do? And that's just the classical protocol we saw. And we reasoned through that, and we saw that she couldn't do any better than 3/4. Yes?
I was going to ask about the meaning of lambda in this case.
Okay.
You said in one case, a classical case, lambda is just the value of bits that Alice sends.
Well, lambda is the ontic state, the complete description of all the properties of the system in some ontological model. So here, there's a lot of generality here because I'm saying this sort of argument is going to apply for any operational theory. So I haven't told you what the statistics are when you do a certain preparation, a certain measurement. I just say, look, there is some description for that. That's the operational theory. And now we're talking about the possibility of underlying those operational theories with ontological models.
Okay, that's what I was going to ask about because we had seen lambda pretty much in the context of ontic interpretations.
Right.
But I thought that we were dealing just with an operational, let's say, protocol or proof. So I wasn't sure how to deal with the ontic lambda in the operational protocol.
Right. Well, it's a bit subtle. I mean, what we're imagining here is a space of operational theories. And then for each of them, we're asking a question about ontology. We're saying, can a given operational theory be have its statistics explained by some underlying ontological model, where every preparation is represented by a distribution over lambda, every measurement is a set of response functions over lambda. So we're trying to distinguish the points in the landscape of operational theories in terms of what kinds of hidden variable representations they admit. And that's exactly what Bell's theorem was. Bell's theorem was a way of dividing up the space of all operational theories into those that do admit of a locally causal model in terms, at the underlying ontological level, and those that don't admit of a locally causal model at the ontological level. So when you say, for example, oh, here's an operational theory, it's Bell inequality violating, then strictly speaking what you're saying is, here's an operational theory, and all of the ontological models that are able to explain its predictions, they violate local causality. So local causality is an adjective that applies to ontological models. Operational theories are not locally causal. Ontological models are locally causal. And Bell inequality violating is an adjective that applies to operational theories. And it's telling you whether there exists an ontological model that's locally causal. And so it's the same thing here. When I say an operational theory is non-contextuality inequality violating, I mean when you find any ontological model that can explain statistics, that ontological model won't be non-contextual. It will have to be contextual. So there's this. This is a sort of a tricky business. You have to bear in mind these sort of two levels of description. And what makes it particularly unfortunate is that people in the field use a kind of a shorthand where we go around talking about operational theories as non-local. And what we really mean is, oh, any underlying model for that operational theory is non-local. And we go around saying operational theories are contextual as well. But we really mean the underlying ontological model is contextual. So that is a bit confusing. So you'll often hear people say, quantum theory is contextual, or quantum theory is non-local. That's a little bit sloppy for the reasons I just described. Okay, so we have this nice inequality now. And remember from last time, we said, well, one of the things we wanted to do with an operational notion was be able to say, do experimental tests of non-contextuality. So here's the idea of an experimental test. You go to the lab, you choose 4 preparation procedures, you choose 2 measurement procedures that are binary outcomes, you calculate the statistics for every choice of preparation and measurement. Then you plug those guys into the formula for the probability of success in this protocol, and you just verify that this probability is greater than 3/4. So given that we think that quantum theory is a good description of our world, we can go to the lab and, to the best of our ability, try to do those preparation procedures which we think are associated with these quantum states. Of course, we could be wrong. Quantum theory might not be the right operational theory. So at the end, we still have done 4 preparations and done 2 measurements. And whatever theory describes them, maybe statistics is different from quantum mechanics. But as soon as we violated this inequality, we've done something interesting experimentally. But actually, I should say, we've only done something interesting if we further verify this parity of Libby's property, because I needed that to show that I couldn't have a non-contextual explanation. And that one's harder to verify experimentally because it asks us, well, first of all, to consider these 2 preparations. That's easy. We just do equal mixtures of the parity 0 and the 2 parity 0 preparations and equal mixtures of the 2 parity 1 preparations. But it also says, check for all measurements that you can't distinguish them. And that's something that's hard to do because typically there's an infinite number of measurements in your model. So what you can do is, for example, in quantum, ideally you wouldn't want to trust anything about quantum theory. And so this isn't quite what we wanted. We would like an experimental test of a non-contextuality inequality that didn't rely on quantum theory at all. But yes, back here I said it's almost independent of the validity of quantum theory. And now I'm going to be talking about that caveat. So one thing you can do is you can say, well, if quantum theory were true, then I wouldn't have to do every measurement. A fiducial set of measurements would be adequate. So we define fiducial measurements in the first week as a set of measurements from whose statistics you could infer the statistic of any other measurement. So if you go to the lab and you do a set of fiducial measurements, then given your belief in quantum theory, you suspect. So suppose with respect to those fiducial measurements, you can't tell the difference between these two guys. Then your belief in quantum theory leads you to think that had you done any other measurement, you also wouldn't have seen the difference. But of course, you don't want to assume quantum theory, so that's not ideal. So you go, you do some more measurements. After a while, you might just develop confidence that there is no measurement that seems to be able to learn anything about the parity in this scenario. Yes?
Maybe I'm a bit confused, but in the context of Bell's inequalities, for example, where we would try to check the validation experimentally, there we also assume that quantum mechanics is right, no? By constructing the way we construct our measurement apparatus uses our knowledge of quantum mechanics, and then so the answer indirectly trusts needs the hypothesis that quantum mechanics is correct or not?
Not quite. If you're doing an experiment where you want to see the maximal possible violation of Bell inequalities, you'll carefully choose how you do your measurement procedure, guided by what you know about quantum mechanics, and you'll think, oh, it looks like I'm doing something close to a z-spin measurement by the lights of quantum theory being correct. But even if I chose my measurement procedures sort of at random here and here, if I got lucky and I started violating Bell inequalities, then you could say I hadn't used any of my quantum intuitions, but I've still discovered that the world is not local. So actually, even though I'm guided by quantum mechanics, I'm not assuming quantum mechanics when I derive that something interesting has happened. But there is a sense in which even the Bell experiment might presume certain facts about the world. Fortunately, in that case, it's not quite just facts about quantum theory. So imagine this. Somebody says, look, I've done this experiment, and I violated some Bell inequalities. And your response might be, OK, well, that's not going to be interesting unless you can convince me that there wasn't a possibility of signaling from the left to the right. So you might say, did you check that for the different choices of setting over here, the statistics, on the other hand, were the same? And my response is, oh, yeah, for the measurements we did, I checked. The statistics did depend on the setting here. And then you say, but did you do it for all the other measurements? Like, you could have done lots of other measurements over there. Did any of those other measurements reveal what setting was done over here? And then my response is, yeah, I did it for a few others, and there didn't seem to be any dependence. And you say, well, did you do it for all of them? And my response is, well, no, I couldn't do it for all of them. Now, so that's very analogous to what's happening here. You can't test for all measurements that there's no information about the parity. But the one sense in which a Bell inequality violation is on sort of better ground than what we have here is that in that scenario, you have a good response to the skeptic. You can say, well, I didn't need to do all measurements because I ensured that these things were space-like separated, and I trust relativity theory. And relativity theory tells me that there are no signals that go faster than speed light. So it doesn't matter what measurement I would have done there. If relativity theory is right, I won't see any difference in statistics. Here, we don't have something like relativity theory to assure us that no information about the parity can reveal itself in the measurement, because these guys are time-like separated. So that's the sense in which these experimental tests aren't quite as strong. OK, so this experiment has been done, incidentally, and sure enough, this non-contextuality inequality is violated while, to very good approximation, this parity oblivious condition is satisfied. There doesn't seem to be any information about the parity that makes it through, and yet we can still violate this inequality. So let's talk a bit about what's mysterious about this sort of phenomena. And I'm going to bring it back to what's mysterious about Bell's theorem. So on the one hand, you have these non-contextuality inequality violations, which suggests that the distributions I use to represent the preparation do have to depend on the preparation context. So there is information at the hidden variable level about the parity, according to this. It's there in the distribution over the hidden variables is different for parity 0 and for parity 1. That's what preparation contextuality tells me. And yet, when Bob tries to extract information about that parity, he always fails. So there's strict independence of the measurement statistics on the preparation context. So even though the information's there and it's gotten through, Bob can't access it. And so this is very analogous to the sort of tension that we saw in Bell's theorem, where our attempts to try to provide a causal explanation of the Bell inequality violations suggest that there really is a causal inference from Alice's lab to Bob's lab. So there's information about what setting Alice has chosen that makes it over to Bob's end of the system. And yet, nothing Bob does can extract that information and bring it to the operational level. You can't send a signal using that influence. So it's sort of the same sort of tension. The information's there, but you can't access it. Here, it's among space-like separated regions. Here, it's between two time-like separated regions. Okay, questions about that?
So to clarify, so you mean contextual preparation is one which, one which you don't have complete access to the ontic state of the system. Is that right? Like you can't have access to the part that tells you about the parity point.
Yes, that in a oops, that's the wrong way. In a preparation non-contextual model, because let me go back one more slide. So let's just see exactly where preparation non-contextuality came in. By the definition of my protocol, I'm basically saying, whatever you've chosen for these four guys, it better be that the equal mixture of 0, 0, and 1, 1 is totally indistinguishable from the equal mixture of 0, 1, and 1, 0 from the perspective of all possible measurements. So I'm asking you, that's a constraint on how you can choose these guys. And in quantum theory, when we choose those four states on the block sphere, we've satisfied that constraint, because the equal mixture of these guys is operationally equivalent to the equal mixture of these guys. No measurement tells them apart. So I basically, in this protocol, force you to build two procedures that really are operationally equivalent. And that's kind of the antecedent to the implication that preparation non-contextuality makes. So preparation non-contextuality is always an inference from if operation equivalent, if equivalent operationally, then equivalent ontologically. So I always sort of need to build in some equivalence at the operational level, and then infer some equivalence at the ontological level. So that's how I got here. And then that equivalence at the ontological level teaches me something about that at the level of my experimental statistics. It says that certain combinations are going to satisfy certain inequalities. So it's sort of a back and forth game between the operational level and the ontological level. Does that clarify things? You could ask the question again if maybe I didn't understand it correctly.
I'll think about it for a bit.
Okay. I should say, I mean, this business about non-contextuality is one of the most subtle things in foundations, and so it takes some time to wrap your head around it. Okay. So you might have noticed that this protocol I just set out had this 75% probability success rate for a classical scheme, 85% success rate for a quantum scheme. And that's exactly what we saw in that game when we were talking about Bell's theorem. So that's no coincidence. There's a mapping between these two things. So I want to tell you about that. And it's going to connect up with some other things we've seen in the rest of the course. So remember what the game looked like. There was two choices of measurement on the left and the right, S and T, and we wanted 100% correlation for those three choices and 100% anti-correlation for the TT choice. And we found that in a locally causal model, you could do at most 75%, whereas if I choose these particular quantum bases, so this for S, this for T, and then diagonal and anti-diagonal over here, then I can get an 85% correlation in these three cases, and 85% anti-correlation, and therefore 85% success rate overall, if we start with this entangled state here. All right. Now, what I want you to do is imagine this Bell experiment now as a steering experiment. So you saw this in tutorial and in your first homework, where you start with an entangled state, you do a measurement on one of the two qubits, and you update the state of the distant qubit. So forget about the measurement device here. Imagine you're just trying to update the quantum state of this qubit over here. So let me draw it in the block sphere. You're choosing to do a measurement of either this basis or this basis, Z spin or X spin, on the first qubit. And your description of the second qubit, well, it starts out as a complete mixed state. That's just the reduced density operator on B for this initial maximum entangled state. So you always start off describing it by a completely mixed state. But if you choose to do this measurement on the first qubit, then you collapse the distant qubit to 0 if you got outcome 0, and 1 if you got outcome 1. So you update your state to describe the second qubit to either 0 or 1, depending on the outcome you got. And similarly down here, turns out this guy here, this state, can be rewritten as plus tensor plus, as minus tensor minus. If I write that out on a 0-1 basis, the cross terms cancel. And so again, if I find plus on A, I collapse B to plus. If I find minus on A, I collapse B to minus. And so I just collapse it to plus or minus, depending on what I got as the outcome of my measurement. And of course, Einstein said, well, if you interpret these guys as ontic states, well, then that's a kind of non-local influence from your choice of setting on the left to the state on the right. All right, what's the interpretation of this? Well, what we saw last week was that there's a really compelling interpretation in terms of psi epistemic ontological models. So for example, if the way you represented that entangled state was this kind of distribution, so each system is represented by 4 ontic states, and this maximum entangled state is represented by, well, you know nothing about each ontic state, but you know that whatever the ontic state of system A is, B has exactly the same ontic state. That's what this diagram represents. And then if you come along to A and you measure, say, the 1 or the 2 versus 3 or 4, so here I haven't drawn them as lines, I've drawn them as 2 by 2s, but this really represents these, a measurement on these 4 ontic states on the left here. Then what you know about system B, it starts out you know nothing, because the marginal over the B system is just flat, right? All of these columns sum to the same. So I start out knowing nothing, but because of this perfect correlation, if I learn that the ontic state on A is one of these 2 guys, then I know that the ontic state on B is one of these 2 guys as well. And if it was one of the bottom 2, then I know that for B it was one of the bottom 2. Whereas if I did this other measurement, I update my knowledge this way or this way. And of course here, all along, the physical state of system B, the ontic state, is at some particular point. Like say it's this point here. I'll write it here. Say it's at this point. Well then, if I do this measurement, I just learn that it's on the left. So I get this outcome. And if I did the top measurement, I just learn that it's on the bottom. So I get that outcome. And all that's happening is I am resolving my information in one of 2 different ways, depending on what I choose to measure on the left. But there's no physical influence from what I'm choosing to measure on the left to what the physical state of system B on the right is. It's just a Bayesian updating of what I know about it. Okay, good. So this is the kind of interpretation that we thought we might be able to have. And now I'm going to try to convince you that these phenomena, Bell's theorem and non-contextuality inequality violations, they actually forbid this kind of interpretation. So as compelling as it seemed, it doesn't fly. So, okay, how does that work? Well, first let me just rewrite those block sphere equations back in sort of algebraic form. So you're measuring either the 0, 1 or the plus minus basis. And what's going on when you update to 0 or 1 is really, you're starting out with this knowledge, and then you're resolving your knowledge to the projectron to 1 or the projectron to 0. So this is like classical Bayesian updating because you're picking out a term in the convex decomposition of your prior knowledge and making that your posterior state of knowledge. And similarly here, you're picking out either plus or minus from your original state of knowledge and updating to that, like you saw in the homework. So how would I want to represent this in an ontological model if I wanted to maintain this Bayesian updating interpretation of what's going on? Well, I would assume that each of these systems, A and B, were described by some ontic state space, whose elements are labeled by lambda A and lambda B. And I would assume that there's some correlation originally between A and B. So in particular, I'm going to make this correlation as strong as possible. It's going to be a delta function lambda A minus lambda B times some marginal on B. And then when I come along and I measure some pair of response functions on A, well, that's going to teach me by this correlation about B. And so I'm going to update my knowledge about B from the original distribution, which I've called nu lambda B. That's just the marginal on B for this sort of guy, to some mu naught or mu 1, depending on which outcome I've got. And if it's Bayesian updating, then it better be that when I resum those guys with probability half each, I get nu. So I'm imagining that I get each of these with probability half. So these probabilities are just the probabilities that I collapse to this guy or this guy. And the idea is that if I'm just updating my knowledge, that I'm going from nu to some element in a convex decomposition of nu. And therefore, I'm just Bayesian updating. Yes?
What is a marginal?
Sorry?
What is a marginal?
What's a marginal? Oh, a marginal is it's jargon for, so if I want the marginal on lambda A, that means integrate this distribution over lambda B. So it's just, when I know about A and B, and then I say, how do I represent my knowledge about A? I marginalize over B. So I just sum over all the possibilities for B, and that just leaves me with the total probability for a given lambda A. So when I said a new lambda B is the original marginal on B, it's basically the representation of what you know about B, forgetting about A. Okay, so that's that must be true if I'm doing Bayesian updating in the ontological model. And similarly, if I do this other basis measurement, plus versus minus, well, that quantum measurement is going to have to be represented in the ontological model by a pair of response functions, which I'll call C plus and C minus. And if it's just Bayesian updating, then it means that that new lambda B, my prior, should update to 1/2 mu plus and mu minus, which are representations of the states I collapse to. That's what we saw in that restricted statistical bit theory. We could achieve exactly this sort of representation. Okay, and now note that this actually is an assumption of preparation non-contextuality. What it says is, let me try to explain it in the following way. Yes. Yeah, let's do it like this. So if I think of this whole procedure, prepare a pair of systems, do a measurement on the first guy, register some outcome. That's a way of preparing the second system, right? Because at the end of the day, that I can then do some measurements on the second system. I have some expectations of what its statistics will be. So I can think of all of that now as just some fancy way of preparing the second system, which is what the right sort of context for talking about preparation contextuality. So if I want to compare this, I can think of this experiment either in the Bell way or the non-contextual way. So as a Bell experiment, I'm just looking at correlations between the outcomes of measurements here and here. So these were the particular measurements I was doing in the Bell experiment we saw. But I could also reconsider the very same experiment as a preparation meets a measurement. So the preparation procedures are these four guys. And they correspond to doing this measurement or this measurement. So if I do this measurement, I collapse, how would I update my knowledge about this guy? Oh, well, I collapse it to either this point or that point. And if I do the other measurement, the horizontal one, then I'm preparing that distant system in either this state or this state. So I am ultimately, by doing those measurements on A, collapsing system B to one of these four states. Think of that as a preparation of system B. So these are my four preparations. Meanwhile, the measurement we do on B is this one here, either this or this. So I'm really just doing this measurement or this measurement on B. But this is exactly the scheme we saw for that parity oblivious multiplexing game, just rotated by 45 degrees. So these were the four kinds of states that Alice submitted to encode her 2 bits. And these were the 2 sorts of measurements that Bob did to reveal them. So the setup, that's at the operational level, how this parity, I believe, this multiplexing game connects to the PR box game you saw. And now, let me try to convince you that the locality assumption implies preparation non-contextuality. So the locality assumption said that, well, one way to interpret it would be the distribution over the states here, the overall distribution, the one where you haven't conditioned on anything you've learned. Well, that can't depend on which measurement you choose to do over here. If the overall distribution depended on what measurement you chose, the only way to explain that, because you haven't, I'm imagining you haven't registered the outcome, you're not updating your knowledge. You're just choosing to set something here or here, and you're not even looking at the outcome. Well, if you would change your description of the distribution quantic states over here in response to just setting a particular outcome over there, that would imply that there would have to be some influence and some change of the ontic states over here as a result of that choice of setting. And so back when we assumed that it was the same nu of lambda b that was getting updated over here, regardless of whether you chose to measure this or this, you were assuming locality. If locality fails, then yeah, these distributions could easily be different. And that's exactly what we assumed in our little prepare and measure scheme. We assumed that the mixture of these two guys and the mixture of those two guys, they were represented by the same distribution over the hidden variables. And those, I wish I had these both on the same slide, but whether I choose to do this measurement or this measurement, that is what determines whether I am doing a parity 0 preparation or a parity 1 preparation. And so the fact that those two mixed states are represented by the same distribution is enforced by locality. Here's an example where the reason I make my distribution not depend on the preparation context is because that preparation context, parity 0 or parity 1, is something that's determined far away in a space-like separated region. It's determined by whether the person over at that wing chose to measure one axis or another. So any dependence on that context would be a dependence on something remote and would be a failure of locality. So is that clear? Okay, so in this particular case, locality implies preparation non-contextuality. We already derived a contradiction with preparation non-contextuality and quantum mechanics. And so, that experiment I just showed you, together with this stuff I just said, gives you another way of proving Bell's theorem. Because in the face of this contradiction, I know I can't have preparation non-contextuality, and because preparation non-contextuality is justified by locality, I know I can't have locality. So it's just another way of proving Bell's theorem via this preparation contextuality business. And what it teaches us is that this steering phenomena actually cannot be understood as classical Bayesian updating of hidden variables. So despite the fact that this seemed like a very beautiful way of interpreting what was going on in those steering experiments, and certainly the way Einstein thought he could explain the steering phenomena, strictly speaking, if you're committed to locality, you can't explain the phenomena as just Bayesian updating in that way. Okay, let's talk. So that's all I'm going to say about preparation non-contextuality. I want to tell you something about measurement non-contextuality now. So remember, we generalized this notion. I'll remind you of the definition. If you have two measurement procedures, M and M prime, they give you the same statistics for all preparations, then you should represent them by the same indicator function, the same response functions. So P, the probability of outcome K given lambda, the ontic state, and M, should be the same as given lambda and M prime. Or in pictures, I should, this is a pair of response functions describing a possible two-outcome measurement. A non-contextual model assigns the same response functions regardless of context. A measurement contextual model assigns different response functions. Okay, so how does this compare with the traditional notion that we saw at the beginning of the lecture on Friday? So you'll remember the traditional notion said if you've got, say, two bases in a three-dimensional Hilbert space and they have some elements in common, then that element should be represented by the same response function, regardless of which basis it's considered a part of. But this doesn't look like the general definition I gave you, because we're not considering here two measurements that are operationally equivalent. These two measurements really are different. There are preparation schemes that will give different statistics for this measurement and this measurement. So how do we connect it up to this notion of equivalence operationally implies equivalence ontologically? Well, it's not hard to do. All you have to do is define a new measurement procedure, I'll call it M, which starts with this basis and then just coarse grains these two outcomes here. And that measurement is represented by a projector value measure which distinguishes the projector of psi 1 from the rank 2 projector onto the rest of the space. And of course, if you define another measurement procedure, M prime, which starts with the other basis, psi 2 prime, psi 3 prime, and then coarse grains them, it's represented by exactly the same projector value measure. And so it's these procedures that are operationally equivalent. There are clearly different procedures, because one of them tells you to do this basis and then coarse grain. The other one tells you to do this basis and coarse grain. So conceivably, you might see different sorts of statistics, but it turns out the way quantum theory works, these two procedures see exactly the same statistics for all preparations. And so we ought to assign them the same response functions according to the generalized notion. According to the traditional notion, we know that the first outcome of this guy is represented the same way as the first outcome of this guy. And then that implies that they should be represented the same overall, because the second outcome is always going to be a response function that just takes up the rest of the space. These response functions have to sum to 1 everywhere in the space. So if you tell me that the first outcome is represented the same way, then I know that the second outcome is represented the same way as well. So that gets us closer to the general notion. But there's still a difference, which is that the most general representation of a measurement is in terms of response functions that are not deterministic. And therefore, this traditional notion we talked about actually is not just this revised notion, the operational notion of non-contextuality for measurements, but it folds in an extra assumption about determinism. It says that the outcomes of measurements are deterministic if your measurement is projective. So that's how I want to think about the traditional notion, as a pair of assumptions like this. Good. That means that the new definition I told you about is not just a generalization of that traditional notion. It's actually a revision of the notion. It's saying that the old notion incorporated an assumption of determinism, and we're trying to take that out of that determinism should be separated from the assumption of non-contextuality. And this should be familiar because at the very beginning of the Bell lecture, I mentioned that Bell started with an assumption of local determinism, where he was basically saying, does the outcome of some measurement depend on space-like separated events? So in addition to the outcome of measurement depending on the local settings local to it, and the ontic state, does it have to depend on events that are happening far away? That was his original notion of locality. But he wanted to be able to talk about theories where things weren't necessarily deterministic. And so he modified it to a better notion that asked whether the probability of the outcome depended on those distant events, in addition to depending on the local settings and lambda. So changing from talking about the dependence of the outcomes to talking about the dependence of the probability of the outcomes allowed him to formulate a notion of locality that didn't assume determinism. And it's exactly the same thing that we've done here. The traditional notion of measurement non-contextuality asked whether the outcome of a measurement depended on the measurement context, in addition to depending on which observable you were measuring and what the ontic state that was fed into the measurement device was. And this new revised notion modified that and just asks whether the probability of the outcome depends on the measurement context. So those response functions that aren't totally flat are specifying the probability of the outcome for a given lambda, a given observable, and we want to know whether it also has to depend on the measurement context. So in this way, you can separate the issue of determinism from the issue of non-contextuality, and my view is that that's appropriate because they're really different sorts of notions. Only this revised notion of non-contextuality really captures that principle that things that are operationally the same should be ontologically the same. The determinism element of it was something else. Okay, but now you have a bit of a problem because all the no-go theorems we saw on the first day, like the Klyachko proof with the pentagram or the Cabello 18 ray proof, those were all no-go theorems for the old notion, the traditional notion. And so they're no-go theorems that follow from this pair of assumptions. And in the face of a contradiction, if you wanted to, you could always say, well, I'm going to salvage this revised notion of non-contextuality by giving up determinism. And so there's a question here. Can we always do that? Can we actually have non-contextuality for projective measurements by only looking at ontological models that are indeterministic? Well, it turns out that you can kind of resurrect the old proofs as proofs of some kind of general notion of non-contextuality, because what you can show is that this deterministic assumption here, this assumption of determinism, it actually follows from preparation non-contextuality. Okay, so in quantum theory. So if you assume the validity of quantum theory, then preparation non-contextuality implies this. I'm going to convince you of that quickly. So go back to our old example of a measurement of the basis in a three-dimensional Hilbert space. And now the proof is going to be by contradiction. So assume that this projective measurement is not outcome deterministic, which means that there's some area on the space of object states where there's a non-zero probability for many different outcomes to occur. Okay? And I'm going to show that this contradicts preparation non-contextuality. So the next thing I want to do is imagine that you're doing an experiment where you prepared, say, psi1, and then you measure this basis. And I want to ask, how do I represent that preparation of psi1 in this model? Well, it's going to have to be with this kind of distribution I've drawn here, a distribution whose support is entirely in that part of the response function for psi1 that has probability 1. Because I know in quantum mechanics that if I prepare psi1, the probability of getting the psi2 outcome in the measurement of this basis is 0. And if this distribution had extended into this region, then the ontological model would tell me that there is some probability of getting the second outcome. And I know that's not the case. Did you have a question?
Since we said quantum mechanics is preparation contextual, I'm not. How can we combine preparation contextuality with validity of quantum theory to get that implication? I mean, you just gave it the proof, but I'm asking about how it's possible to put together those ideas.
Well, I guess the broader point is that impossibility results have a logical structure. I can talk about the logical relations among different things. So we know that you can't have a preparation non-contextual model, which is the proof I showed earlier. And now you can ask the following question: are those old no-go theorems for the traditional notion of non-contextuality, like Cauchy-Specker's 117 rate proof, are they also somehow demonstrations of the impossibility of a non-contextual model? And so what I want to show is that yes, they are. That so anytime you do a no-go theorem, you have to sort of imagine that a whole bunch of assumptions hold, and then derive a contradiction. And so what I'm saying is that these assumptions, validity of quantum theory and preparation non-contextuality, imply this. And then so if I can derive my contradiction from this together with measurement non-contextuality, then I've shown that something has to give, like either preparation non-contextuality or measurement non-contextuality, and so on. So I'm I know that these things are invalid, but I'm really just trying to find out what the set of all possible proofs of that inconsistency look like. And so I'm going to show you that all those old no-go theorems can be re-enlisted as no-go theorems for this generalized notion of non-contextuality that incorporates measurement non-contextuality and preparation non-contextuality. Okay, so let me continue with the proof. To explain that when you prepare one of these guys and then do this measurement, explain the fact that you only get the psi1 outcome for psi1. You need this guy to be confined here. You need this distribution to be totally confined to this region. And so in this case, all these three of these distributions stay out of this yellow region here. However, I know that there's some state on the Hilbert space whose distribution over the ontic states does have some support in this region. And if there weren't such a state, well then I could just eliminate this region of the ontic state space and have a new ontological model that would have outcome determinism for the measure. So there's some state in the space that has that support. And now here's the critical point, that if I mix these three preparations, side 1, side 2, side 3, with equal weights, I get a preparation of the complete mixed state, identity over 3. And it's also true that I can find two orthogonal partners to any state, psi, such that if I mix all three of those orthogonal states, I get a completely mixed state over the number space. And now preparation non-contextuality tells me that I should assign the same distribution over lambda for that completely mixed state, regardless of how it was formed as a mixture of other states. So mu identity over 3 should be written, should be possible to be written this way, or as 1/3 mu psi plus 1/3 of each of the orthogonal effects to psi. And now I have my contradiction, because the right-hand side of this equation assigns probability 0 to this region, whereas the right-hand side of this equation assigns non-zero probability to this region. Okay, so what it means is that because of this inference, when I take the general notion of non-contextuality, the operational one, which is both non-contextuality for measurements and preparations, well, then I can derive the traditional notion, because this guy allows me to derive outcome determinism, and the traditional notion just is the combination of measurement non-contextuality and determinism. Okay, so no-go theorems for that traditional notion can be salvaged. There's no-go theorems for the generalized notion. But furthermore, you get some new proofs coming out, because as we saw late on Friday, even a given POVM can often be implemented in one of two different ways. That's a notion of context, measuring context, that it wasn't around for projective measurements. In a two-dimensional subspace, a two-dimensional Hilbert space, if I give you an array, there's only one measurement that it's a part of, which is the pair of orthogonal arrays associated with it. So for projective measurements, there's no notion of context in 2D. Basically, there's only one measurement that has a given array in it. But if you look at POVMs in 2D, well, now you can still think of one POVM as arising either by a convex combination of these guys or a convex combination of those guys. And so now, even in a two-dimensional space, you have a non-trivial notion of context, and it can be shown that using that non-trivial notion of context, you can have a proof that at the hidden variable level, there must be dependence on that context. So whereas the old traditional approach had proofs for 3D and greater, you can get proofs in 2D by just broadening your notion of what a measurement context is, and then of course you have to sort of see the details of the proof, but I'm not going to present it here. Okay, well, I've kind of run out of time. Let me just wrap up. So there's one thing that remains to be done. So in the case of preparation non-contextuality, I sort of talked about an experiment you could do wherein you could conclude that even if quantum theory is wrong, whatever ontological model underlies the operational theory that describes the world, it has to be preparation contextual. The question is, can we do that for the notion of non-contextuality that's associated with measurements? So is there some experimental test of contextuality that focuses on measurement context rather than preparation context? And the problem is that that inference I showed you from preparation non-contextuality to outcome determinism, that was only in the context of quantum theory. That wasn't a fully operational justification. So if you wanted a fully operational justification of that, you would need, first of all, to have some sort of general notion of what a projective measurement is. So projectors are part of the formalism of quantum mechanics. So you'd have to have some sort of operational notion of what stands in for projective measurement. Those are sometimes called sharp measurements. And then you would need to justify outcome determinism for those. So you need to rely on the facts about these measurements and show that preparation non-contextuality in this operational theory would imply outcome determinism. And only then could you use some of these inequalities we derived at the beginning of last time, for like the triangle and the pentagram, and go to the lab and test them, and if you see a violation, you know something strange is going on. Because all those inequalities relied on an assumption of outcome determinism. We haven't really justified that yet with an assumption of non-contextuality. So that's sort of where things stand. That we're sort of missing some description of facts about sharp measurements and general operational theory, such that we could derive this determinism and turn all of those old inequalities into things that we can really test in the lab. All right, well, I've gone over time. The last thing I was going to tell you about was to connect all this business to Wigner representations, but I better end, so maybe let me just jump through it. Sorry. The key point was this here. Yeah, let me just say this. That in addition to the Wigner representation, there's some other representations of quantum states and quantum measurements that go by the name of quasi-probability representations. So like the Wigner representation, they're real functions over some space. They're not necessarily phase space, right? So Wigner representation is a function of phase space. But like the Wigner representation, they're allowed to go negative. And that's why they're called quasi-probability representations. Because if there were probabilities, they would be everywhere positive. So the general definition of a quasi-probability representation is just some function over some space. So called this is a space, like a phase space or something else. A quasi-probability representation associates with every density operator some real function on that space, which integrates to 1. It associates with every POVM some set of functions, which, when summed over k, give me 1. So had they been positive, they would be response functions, but they can sometimes go negative. And it reproduces the predictions of quantum mechanics using this formula. Now, this will provide a classical explanation of all those statistics if those functions are positive, and these response functions are positive. So if you had non-negativity in your quasi-probability representation, you would have a classical model. But it turns out that what I've defined here is exactly this general notion of a non-contextual ontological model. Because an ontological model assumes distributions over some space, and it assumes response functions. And the assumption of non-contextuality has been built in right from the start, because it says the function depends only on the density operator, not which pure state ensemble prepared that density operator. Or it depends only on the POVM, and not which projective measurements you mixed to get that POVM. So a quasi-probability representation had non-contextuality built into it from the start. And if you wondered at some point, why anyone would assume non-contextuality, why is that a natural assumption, then bear in mind that anybody who came up with a quasi-probability representation was implicitly making that assumption, often without even noticing it. So you'll read a lot of papers that just sort of start from this point, without explicitly mentioning, oh, by the way, that means that we're not allowing different pure state ensembles to be represented differently in our model. So it's a very natural assumption. And so the point is that you might have wondered, well, the Wigner representation, it goes negative, but maybe there's some other representation that stays everywhere positive. Wouldn't that be nice? Because that would give us a way of understanding everything classically. Well, the fact that we can't have a non-contextual ontological model, which we've just proven earlier today, implies that we cannot have a non-negative quasi-probability representation either, because they embody exactly the same notion of classicality. That's also a reason why this general notion of non-contextuality is kind of nice, because it dovetails nicely with a very different notion of classicality that people in quantum theory have had, which is this notion of non-negativity in quasi-probability representations. So let me end there, and I'll take the question. Yeah?
But it would be possible then if we would modify the link between, for example, POVM and psi, E, K, flum.
Yeah.
But then you would not call it probability representation theorem anymore? Or, like, say you would allow the measurements to, that what the measurement does depends on the state it gets. Say you would allow that. And then you would maybe get a positive probability representation from the mechanics. Would you still call it probability?
Part of the definition of these quasi-probability representations and ontological models is that all the information about the preparation procedure that makes it to the measurement device is encoded in lambda. So in the language of Markov chains, the preparation procedure, the ontic state, and the measurement outcome, they form a chain. The ontic state is supposed to screen off the preparation from the measurement. So there's no direct causal influence from the preparation procedure to the measurement procedure. It's all via lambda. So if you wanted an explicit dependence on the preparation here in the response functions, you'd be giving up on that definition of the ontic state. And yeah, you could, well, I mean, I guess the point is that you could always have chosen an object state space that encodes rho entirely, right? It's allowed to depend on rho. So I think that would be like a kind of, not just a psi-ontic model, but a rho-ontic model. So the, the whole density operator encoded in the physical state of the system, and the measurements are allowed to depend on that. You can generate the quantum statistics that way, but it's highly preparation contextual. Because, for example, if I talk, if I say, okay, here's a z-spin state, what's the distribution on the hidden variables? Oh, it's on the Bloch sphere, it's a distribution that's just peaked at the North Pole. What about the z down state? That peaked at the South Pole. And now you say, well, what about the completely mixed state? Well, that might be peaked at the center of the Bloch sphere, or it might be a uniform mixture of the peak at the North Pole and the peak at the South Pole, depending on how you prepared it. And so the distribution you're using now depends on the particular preparation procedure associated with the mixed state. So this doesn't say that you can't generate the quantum statistics. It says you can't do it and hold on to this non-contextuality assumption. Yeah. Okay. So next time we're going to get into the interpretations that we talked about on the first lecture, and we'll start with the de Broglie interpretation.